Hi there, and welcome back to our hacking series. We're still looking at the Foscam R2C IP camera, and if you haven't seen the last 3 episodes, please go back and check those out, or you might be a little lost. In the previous episodes, we were able to gain access to the console through just identifying the UART pins. We were able to find the U-boot password online and gain access to U-boot, which in turn gave us root access on that same console that we found previously. And then we were also able to dump the flash. So we had access now to some of the software components and all of the partitions on the device. So in this episode, we're gonna actually extract some of the partitions in a little more clean of a way, actually make modifications to some of those partitions to have our changes be persistent now, since we'll hopefully be able to modify the RAM disk that gets booted up. And then we will start to flash that back onto the device. And then we will continue by starting to actually build out the beginnings of an exploit that we can actually upload remotely and hopefully hack this device without much user interaction. So I hope you stay tuned in for this episode, and we'll catch you at the end. And since we still have the Raspberry Pi hooked up, we could potentially just flash the image back onto the device. And I remember when we were diving through one of the extracted files, I found something called the Boot.sh. If we look for that here, Boot.sh, you can see that inside of one of the SquashFS root, there's a Boot.sh, and this, from what I can tell, looks like it is just booting up the device. And since we noticed that we were actually in a RAM disk before, and all of our commands kind of stuck for that one session and didn't actually persist over reboots, this could be a great way to actually potentially modify this script with something that we are interested in or want to do, and have it actually persist through reboots, because now it's going to be running this from the flash, this boot.sh command. But it is kind of hard to actually go through all of the how binwalk extracts all of it. It's kind of a less precise method of just extracting what we want. And so now that we know that it's actually in the SquashFS root MTD partition, if we binwalk our dump.bin, we can actually try to find that in here. And I think it's, like right up here. So right off this is that SquashFS partition potentially. And to do this in a little bit more precise way, to actually extract that SquashFS root without using binwalk, we can actually use DD. So we'll actually save off this offset. So this is the offset into the dump.bin file of where the SquashFS partition starts. So it starts at this offset. So I'll just copy that. And then inside of, we could either check from this address to see how big that, since this is the next thing that binwalk identified. So we can just do that real quick. Let's just actually, so if we take that second number and minus the first number, which is so this is the next thing inside of that binwalk identified, and this is the offset of the SquashFS. And if we see what that equals, that's 96, that's the size of that chunk, but it might not be the real exact size of the SquashFS partition. One of the things that the SquashFS does is actually says its size. So you can see that its size is actually 9516469, so a little bit smaller than the allocated space. So I bet there's probably some null bytes or something padding from the SquashFS to this next XZ compressed data that binwalk identified. And that's kind of, so if they make a firmware update or whatever, and they flash it to this device and it's actually a different size, they have some padding. So we'll actually copy this out. So this is the real size that we actually want to care about. and we can exit out of here now. And so to do this, we'll actually have to look up the DD man page real quick just to kind of see the options we have here. So we will send in, the input file and the output file, which read from file and then output file. And we also want to actually do one of these seeker skips. And it looks like we want to skip, since we're actually going to skip from the input. The other one is skipping from the output. So we'll do a skip. So now since we know the sizes and where that is, the SquashFS partition is inside of this bin file, we can do dd if equals dump, and then we can actually do output of SquashFS, and then this is that offset that we got, and then this is actually the size, and then the block size will just be 1. That's just saying the count is 1 byte. So now we're going to do this many bytes, which will line up perfectly. So if we go ahead and run this, we'll see that now we have this SquashFS.SQFS. And if we bin lock this, we'll see that all it comes up with is a SquashFS partition. So we've kind of like precisely extracted this file system from the greater dump file. And now that we have that, we can actually, instead of using binwalk again here, we can actually use what binwalk is essentially using in the background, which is the SquashFS tools. So we can actually do unsquashfs SquashFS.SQFS. And if we do this, you can see that it extracted 412 files, 34 directories. And if we now see what's in our SquashFS root, we have the mtd, and in here we have the Boot.sh. And this is the file we actually wanted to modify. So if we modify this file with something, so let's just kind of like scroll down until we see something that we could potentially use. This touch mtd debug could be interesting. Just scrolling down. It's mountain stuff. So we can maybe just append our script or whatever we want to the end, or if we see anything that we want to modify in here. So this is like logo stuff. Update version number. I thought I saw somewhere in here that there actually was like a Telnet. Yeah. So Telnet is, I'm glad that it's blocked up. This is like kind of the predecessor almost to SSH. So it's less secure. It doesn't, I don't believe it encrypts all traffic, but if we actually enable this, we'll now be able to like log in remotely to this camera. So let's definitely leave that enabled. And then just to like print out something on the screen, since we have that console access through UART, let's try to actually add like an echo, and just to make it more visible on the screen, we can do like 50 dashes and then do hacked, and then 50 more dashes. Sweet. And I don't know if the console is actually only printing standard error or standard out and standard error. So like, I'm just gonna do this exact same print message, but redirect it to standard error, which is 1 into the address into AND2. So this will redirect standard out into standard error, just in case that it's not printing out, just regular standard out. And then one other thing we want to do is actually change the root password, because Telnet can either be set up to not ask for a password or ask for a password, and I just would rather also have root access. And like we tried before when we actually ran the password command, it seemed to work for that one instance, but it didn't persist. So if we can add it to the script, that would be awesome. And to do that, let's just try it out in like BusyBox. So if we run BusyBox again, and then password command, see, it asks for the password like twice. So if we do, so it asked twice and then it changed the password. And to automate this, I think we can go echo. If you do -E, it should. I don't think there's a man page for that, but man echo. If we do -E, it interprets backslash escapes. So we could potentially do echo -E, give a password /n, which is a new line. So we'll simulate hitting enter. And this should change the root password to Tor if we pass this into password WD. So let's double check. And yeah, so it passed both those Tors with the new line in, and it satisfied the retyping of the password. So I think this will work. So we'll copy this off too, and then add this before the Telnet starts. So now we'll be able to identify if the password is changed, and then Telnet will start, and we could potentially use this password to log in as root. So now that we've modified that file, we need to recompress it or remake it into a SquashFS file to then precisely inject back into the original dump bin. And to do this, we can actually use make SquashFS. So unsquashFS is the extracting, make SquashF is the compressing of that. So let's just bin walk this one more time to see what we're working with. So it is version 4, compression XZ, and then it has the size, inodes, and stuff like that. So we're going to try to make ours match this as close as possible. And so we can do make SquashFS -help and just kind of see what we got here. So XZ was the encryption, or the compression that we had. So those are, that is what we'll need. From the extracting of that one, it looked like root owned all of the files, so we can potentially pass this command in, and then compression XZ. So let's just give that a go and just see how that works, like compare it to that. So make SquashFS -all root -comp XZ, and then we give it file system, source, then file system. And options come later actually. So source we actually did this wrong. So source will be the previously extracted SquashFS root. Then we want to make it new SquashFS.sqfs. and then these options. So let's see if this works. Okay. So now if we bin lock this, the original one, and then bin lock new SquashFS, we're gonna compare to see if there's any differences. So Little Indian, version 4, XZ compression. Ours is a little bit bigger, it looks like now. But that's fine because we saw that there was some gap between the next thing that binlock identified. So I'm not too worried about that. 446 inodes, so there's the same amount of files and the block size is the same. Obviously the created dates are different, but that's perfect. So hopefully the system will be able to use this file system that we've just modified correctly if we can flash this back to the device. To do that, we'll first have to put it back into the original over like the whole flash image. Since we're going to flash it back with the Raspberry Pi, we're not going to be able to just flash this one partition. We're going to have to flash the entire chip. So we'll first copy the dump bin into like hacked dump.bin. So now we have the hacked dump.bin. We'll dd. The input file now is going to be new SquashFS. The output file is going to be hack.dump.bin. And then we're going to copy the size, which is now changed. So we'll do BS equals 1. So the box size equals 1. Count equals the new size. And now if we remember, we'll have to, instead of using skip, I think we'll have to use seek. Since we're trying to inject it into this precise spot of that file that already exists, we're going to actually seek the amount of bytes from the offset. So we'll now seek, and that will be what we grabbed from the bin lock, which was SquashFS, this one. So this will be the offset. So now, if we run this, hacked.dump.bin should now include our new SquashFS that we just modified and look almost the exact same as the previous one. So if we now bin lock hacked.dump.bin, it looks different. Oh, it looks like it got truncated. So all the beginning looks the same, but the ending looks much different. We don't have any of these zlibs and stuff, so it truncated after our SquashFS. So I think there's a way. Okay, so dd, do not truncate the output file. So we'll want to run that, and that looks like you add that to conv symbols. So we'll add cons equals no trunk. Okay. ddif new SquashFS. Oh wait, we'll actually have to copy that one back over. So cp dump hacked again, just because now we want it to be have all of the stuff that got truncated before. And now we can do dd no, that's wrong. So dd input, which being new SquashFS, and then add this com no trunk at the end. Okay. So this now should just precisely overwrite only the bytes that we want, overwriting the old SquashFS partition with our new one, and not have overridden anything else that we didn't want. So if we now bin walk this, it still truncated it. Oh, it's hacked and hack. Oh, geez. Hack. Okay, that looks good. The hack one was the one that we ran last time, so let me just remove that. So now you can see that there is SquashFS here that was created, today, and it's the right size, and this starts at 811. And let's just double check if we bin lock the original that we didn't overwrite anything. So this one, and then the next one starts at 811 too. So now we've injected the SquashFS into our flash image. Now all we need to do is have the Raspberry Pi flash it back onto the device. So let's SSH back into that Pi. Before we do that, we should probably grab the file. So cp hack dump. Okay, so now we have this hacked one. Let's repower up this flash. So now if we run this, it should find it. Found unknown flash chip. Cool. And this time, instead of -R, we're actually going to do -W hacked in. And we're in this problem again. Unpowering, powering, running. Unpowering, powering, running. I'm gonna try to unplug. I'm wondering if it's like keeping power somehow. Aren't you working? This has been so inconsistent. Very frustrating. Oh, it's because the bus power was potentially plugged in, causing it to keep power to the device, potentially. So it finds it there. definitely lost this one. I think that was SCLK. Need some light in here. It's dark. Okay. Yeah, much better. Except I stared at the light when it turned on. Maybe I should unpower this. Okay. That one fell off, and now it's on. Last time I just like unplugged the Pi and plugged it back in. Okay, there's no power to the camera or the Pi. I'm plugging the Pi back in. Wait for the Pi to come back up. Okay. Why isn't it finding the chip? Oh, shoot. Uh-oh. Froze again. Unplugging the Pi. Plugging it back in. Okay. We're in. Why? Like, did this get disabled? That better not have been it again. Okay.
Okay, I'm just gonna go ahead and I don't know, unplug everything again, and hopefully plug it all back in and have it magically work. This is definitely not the most robust system, but okay. So unplug all of this garbage. Okay. Okay. All right. So here's what we got. I got the Raspberry Pi, this little flash chip. Who's gonna start off with we'll end with power. So we'll start off with, I already forgot the Raspberry Pi's pin out. Okay, so the top one is master out, slave in, and that lines up with number 5. Okay, here we go. The next one on the Raspberry Pi is master in, slave out. So that's this one. So blue down here goes to second most one. Okay, that looks good. We got, I'll do ground. Ground is gonna be this yellow one. Oh no, this thing's all bent out of shape. Okay, ground is hooked up. Need chip select, so that is chip select. Chip enable, I think maybe. So you want to cross from, yep, this green one. All right. We need S clock, which is this green one. And that goes to the one right above data out. Okay. And the last one is power. now. Run it. Oh, the Pi froze again. I think. Maybe it didn't. Maybe it just hung the process a little bit. Oh my gosh, it's working. So I'm wondering when maybe the Pi actually hangs. I just need to reconnect on SSH and rather than reboot it. Cool. Well, this took forever last time, so I'll probably speed through this. Alright, it looks like it finished after like 30 minutes. So this time I have to read the old flash, erase, and then write the new flash, and then read the flash again. So definitely took longer than it had previously. Just gonna So now that it's flashed, let's give it a boot potentially. So I'm just gonna unplug everything from the Raspberry Pi. So I don't think we need any of these anymore. Okay, move the Pi out of the way. Okay, this thing, we're gonna plug it back into the bus pirate for UART. Let's get UART all booted up. So, don't need the Pi anymore. Minicom. 3, 9, 2, W1 for transparent mode. All right, now booting it up. We shouldn't have to do anything else, and hopefully we see our hacked line get printed on the screen here at some point. Oh, hacked. Changing root password. Password changed. Yes. Except for this doesn't look good. There's a lot of... I don't remember seeing this many errors getting populated, but okay. We did see our where is it? Hacked. So I guess both of them print to the console, so we didn't need to pass standard out. But anyway, we changed our password. So let's try telnetting in. So telnet what is this thing even? Oh yeah, 75. Root tor. Woo! So we're in. There we go. We got root access remotely. So we want to see if we can send this an upgrade and what actually happens on the device, and see if we can modify anything over here. And we can kind of do this in a similar way by potentially just using BusyBox to see, like in a Docker image, for instance, to see like what we would do. So let's go back over to the terminal. Let's just see what BusyBox we're running. Okay, BusyBox 1241. All right, I think we can run that. Okay. That looks similar, right? Yeah. There's this 2018. This one's 2016, but it's the same version number. Cool. So we could try to make a tar file or an upgrade file, for instance, and see if we can try to make something happen. So if we go to our extracted, our firmware update, original, here we are. So this is the R2C. Here's all the stuff that was in the original. So in the temp, oh no. So it's kind of hard to see what was actually extracted from this. So I'm just gonna go ahead and remove everything that ends with .xml, everything that ends in MD5, and everything that ends in sign. Clear, MTD. So anything that ends with SquashFS. Update. Tab. Up.k. Okay, so I think this looks good. So let's just tar f-c temp plus okay, so at least it's all consolidated here. So I don't think, if all we need to do is actually have that patch file, maybe we don't even need to have any of these files. So this one actually has a firmware upgrade config. Let's just go see if we can find that. So I'm wondering if it, it's weird that I think it exits here. But I guess it runs firmware upgrade here. But still, this one doesn't look like, so when it's not a patch file, this gets set to 0. And when that doesn't hit this, it goes into here anyway. So I still think we want actually a patch config. So I think we're on the right path still. Let's make a folder called hack, and then cd into hack, and then make that patch upgrade config.xml. And let's just, I don't know, foobar. Doesn't even need to be real XML, I don't think. So that will be good. And then I want to try to do, so this is, like I said before, this, we are recreating this in a way. So I actually didn't realize this when I first went around, that the tar-c command is actually quite robust. However, this version of BusyBox does allow for an exploit that I didn't realize at the time. So it's been patched, so it's not a 0-day at this point, but I didn't realize that you can actually add a folder. So like if we go like ln-s and go, yeah, root, I guess. Like if we're trying to overwrite something, let's just do root etc password. No, let's not do that. Let's just do root and then make a that is called like sim. Yep. Okay. So now we have a symlink that we can now actually add a file. So when we tar this, so we can go let's do this inside of the BusyBox. So docker run BusyBox and then give it -vp these spaces and names. Okay. So now if we actually just like tut or echo, this is a demo to root hacked.txt. And now if we tar cv zf, because they use the z command, hack, yep, and then also, wait, how was theirs? Oh, theirs was in the parent directory, so star, and then also sim hacked.txt. Shoot. Forgot to give it a name, so dot. Okay. So if we look at this tar, how do you just print out what's in the tar? list. I don't know why that's going so slow. Let's just do it from the real Linux. Okay, so you can see that there's the patch upgrade config. There's a sim and a sim linked. So it doesn't show that it's a sim link, but it is. And then simhacked.txt. So if we now are inside of this and remove the hack.txt, so now if we ls the root, there's nothing there. But if we do pretty much the exact same command that they did for theirs, so let's see if I still have it. Okay, and it was ddif hack date.bin, pipe that into this, and then pipe this into tar x what was it, x or z xf dash c temp fw upgrade. That folder might have to exist before this, so alright, so this is pretty much simulating what they had. Let's see if our little symlink trick worked. Oh, well, we didn't encrypt it, so we can just delete this a little bit because we haven't encrypted it yet. So can't create directory. File exists. Oh, because I left this bit in. Okay. So now if we ls our root, you can see that there's hacked.txt there. That is actually a vulnerability inside of this BusyBox implementation of tar. Didn't realize at the time. I thought that was just normal operation. But we can use this quite a bit to our advantage. So being able to overwrite any file or place a file anywhere on the system. So like for instance, let's just see etc here. Etc host name. So let's just cat out the host name. It's this, right? So just some random numbers. We can modify our tar to actually overwrite that too. So we could go hack. So we'll actually have to edit it on this first. So let's just change this. So I'll write it for this one instance. So now we can do tar z cvzf star sim etc host name. We need to give it the path again. Update.bin. Okay, and then let's just change this back. So if we cat out the host name now, it is back to what it was, 4.1, 4F1, what you would call it. So just some random numbers. And if we check out here, if we now rerun this tar command of the extraction, which I'm just gonna find it. Yeah, this one. Into the firmware upgrade file. Can't remove old file. Resource busy. Huh, I thought that would have worked. Oh, is it? No. Well, anyway, even being able to just place files arbitrarily is important. And I'm pretty sure that you can actually overwrite files on the test system. So let's just try uploading the original one where we just had the hacked thing. So vim hack.txt echo okay. Whatever, tar cvzf hacked update bin star sim hack.text. Okay, so this is gonna have the hack.text. So theoretically, we can upload that to the system and see what happens. So let's go on over here, change this to the one that has this, what should we call it, software. So you can also browse. So let me just drag this file that we just created onto that project, or onto that VM. Okay, so now that we have that binary, let's try to upload it. And 1 second, we have to also reconnect. ls. Okay, so this is gonna run every 2 seconds. So we can keep an eye on that when I go ahead and hit this firmware update with our hacked bin. So I'm gonna click system upgrade. It's gonna be starting to work. Let's watch this and see if that hacked text gets extracted here. And the connection got closed. Okay, so why is it doing that? It seems to be calling like reboot like pretty quickly. That's why the connection gets closed. So how about we try to overwrite something that's more impactful than just like adding a text file. And let's also check the logs of what's happening. So, okay, here's the boot. This might be this new boot, so hacked. Cool. Yeah, I think that's the same boot. So let's go back before this one. Okay, so this is the beginning of that boot. So we're trying to find tar invalid magic. Well, that's not good. We want real magic. So our tar file might be tar short read. Records in, records out. Invalid magic. Why are we getting invalid magic, huh? So, if that doesn't make sense to you, every file has like magic bytes that can help because Linux doesn't actually care about file extensions at all, if you're unaware. Unlike Windows, where they actually use the file extensions for things, which is odd to me. Linux uses inside of files, they have like PNGs, for instance, have a certain 4-byte string inside of all of them that you can search for and identify that it's a PNG. That's exactly what actually binwalk is doing. It's going through and searching for these magic bytes. So the tar file has invalid magic. Oh, it's because we didn't encrypt it. Remember? The black box. So we actually have to encrypt it. So let's do that now, actually. So we have this hacked update bin, and if we list that out, we have those. So let's actually take the inverse of the this encryption command and actually encrypt it. So instead of D, it's an E. Yeah, that looks right. Cool. This should be what we actually need to upload. So let's go back to Telnet. There's a way to make it watch faster. Maybe that's a good thing too. Interval n. Let's do watch n 0.5 real quick. ls hack.txt. Invalid number. All right, 1. So every second now it's going to be catting that out. And if we go to our VM and choose actually the encrypted binary system upgrade, go back here, we should see that not say no such file at some point, hopefully. What? It still just rebooted before it could do anything. But if we go back to here, let's see why. See if we got at least valid magic. So this is this looks like the output you get from the OpenSSL command. Oh, that might be a different time. Okay. Patch tar. So it decrypted it. So it looks like it's trying to find a patch.tar.xz. Where is it trying to find that at? Let's go. Patch.tar.
There you have it, the end of the 4th episode. Hope you guys enjoyed it. In this last episode, we were able to re-flash the device with our modified partition. We were able to have now our root password be persistent, as well as actually remote access through Telnet. So now we can log in with the root account through either the local UART console or remotely through Telnet. So that was pretty cool. We also started to create a malicious update, and we'll continue that next week and hopefully get a full working exploit. So if you want to see the fruits of all this labor, please tune in next week for our final episode, and we'll see you then.